Let's solve Schrodinger equation for hydrogen atom. Let me recall equation 1, which tells us about the time independent Schrodinger equation, because we do not have any time factor into this equation. Schrodinger equation tells us whereabouts of a particle and what will be its future. This equation tells us energy of the particle too. For example, in order to solve the Schrodinger equation, that is equation 1, we need to put the exact form of V, that is the potential. If we talk about hydrogen atom, in hydrogen atom there is no neutron, only a proton is there. So there is one plus charge, there is one electron on the outer orbit. So here one plus charge, one minus charge. Between these two charges, Coulomb attraction is there as they are opposite in sign. Coulomb force is 1 by r square force, so Coulomb potential must be 1 by r type of potential. This is general form of the Coulomb potential, which says Vr, that is potential between two charges q1 and q2 separated by a distance r. Epsilon 0 is the permittivity of free space, and the Coulomb potential takes this form. Q1 we have Ze, Q2 is E. Z is equal to 1 here because we are dealing with hydrogen atom, there is only one proton. So if we put Q1 equal to Ze and Q2 equal to minus E, that is charge of electron, charge of the nucleus. Here Z is equal to 1 as this is hydrogen atom, so we get Q1 Q2 equal to Ze square. So my equation 1 becomes E psi equal to minus h cross square by 2 m d2 psi dx square minus Z square by 4 pi epsilon 0 r. As I am trying to find out a general solution for atoms, so we are not going to put Z equal to 1 for the time being. I'll carry this Z. Now let me solve this equation in a slightly different way. Generally we need to solve it like this is in Cartesian coordinate system and this is in polar coordinate system because r is there and x is there. So this is in Cartesian coordinate system. For higher order terms we need to write d2 psi dy square, d2 psi dx square, etc. One term is in polar coordinate, other terms are in Cartesian coordinates, so we need to switch over the coordinates, make a transformation between the two coordinates, but that's going to be a little bit complicated. Here I am going to solve it in a somewhat different way. First I will use this equation which tells me that total energy equal to kinetic energy plus potential energy, and kinetic energy is half mv square, potential energy as I have just mentioned that minus Z square by 4 pi epsilon 0 r. Another term I am going to use which is a centripetal acceleration, which is acting outwards, pushing the electron outwards. Because of its circular motion, centripetal force comes into play. As there is force, there is acceleration, but this centripetal force is of course balanced by the Coulomb force, which is attractive in nature and acting in this direction. So by balancing the two forces, centripetal force is mv square by r, this is Coulomb force Z square by 4 pi epsilon 0 r square. This is my centripetal force mv square by r. Now I have made a video on in my waves series that as the electron is moving in circular orbits, so it must lose its energy and eventually it falls, it jumps onto the nucleus, which means the structure of atom must be very fragile. But this doesn't happen in nature. Atom is a very stable kind of thing. So what happens here, In order to explain this stability of the atoms, we need to consider electrons as waves, not as particles. So there are waves associated with the electron. The wave is like this. It is spread in the entire circumference of this circle. Length, that is length of the perimeter of the circle, is L, and if the distance between this nucleus and electron is small r, then L is equal to twice pi r. For wave, we can write this wave function psi x equal to the power I kx. There is no need of omega t term, no need of time term, because this is a standing wave, this is not going anywhere, this is not a progressive wave. And after one complete revolution, the electron again comes here, and in the meantime it has already traveled the distance of L meter. So these two wave functions at this point is psi x equal to the power I kx, and after traveling a distance of L, the wave function will look like it to the power I k x plus L. This is I, this is not j, and this should be equal. This is actually what gives us the idea of quantization of angular momentum. So as the two waves are equal, to the power I kx equal to the power I kx plus L, I kx cancel out. What I get is e to the power I kl equal to 1, e to the power twice pi I equal to 1, because e to the power I theta is cos theta plus I sin theta, sin twice pi equal to 0, cos twice pi is equal to plus 1. So I have e to the power I kl equal to the power I twice pi, which gives me kl equal to twice pi. And this is true, this will hold, this will hold for if cos theta, that is theta, is equal to 0 or twice pi or 4 pi or 6 pi, etc. So I can write kl equal to twice pi n, where n is an integer, of course. N can take value 0, n can take value 1, because then kl equal to twice pi. N can be 2, because then kl equal to 4 pi n. It could be 3, and so on. So these are the values, these are the integers values n can take. Now what is L? L is of course equal to twice pi r, that is the length of this circumference. So from this equation, L equal to twice pi n by k, I will put L equal to 2 pi n by k, which is equal to 2 pi r, because L is nothing but 2 pi r, and L equal to 2 pi n by k from this relation. So I am equating 2 pi n by k equal to 2 pi r, which gives me k r equal to n, and n is quantized, because n is equal to 0, 1, 2, etc. N cannot take just what I like value. N can't be 1.5, it can't be 1.7, it can't be 2.08, etc. So here kr is quantized, which means k is quantized. We also know that p equal to h cross k, k is equal to p by h cross, which means if I substitute the value of k here, I will get quantization of momentum. So we have PR equal to NH cross. PR is nothing but the angular momentum. This is linear momentum into distance, which means this is angular momentum. So this also contains N, because H cross is a fixed constant, reduced Planck constant, H cross equal to H by twice pi. This relation tells me that angular momentum is also quantized. P equal to mv, so it's mvr equal to nh cross, and I'm going to use this equation 3 also. So here comes the angular momentum quantization, which tells me mvr equal to nh cross or pr equal to nh cross. If we further proceed, if we make a square, both sides of equation 3, I'll get m square v square r square equal to n square. Now if we remember equation 2, which tells us that the centripetal force balances the Coulomb attraction, we have the expression of v square from this equation. So let's put the expression of v square into equation 2. I get this equation, and from some algebra, very simple process indeed, I got r equal to this much. So r equal to epsilon 0 h square by pi m e square n square by z. This is a constant, this is Planck constant, pi e is a constant, m is constant for a particular atom. E is the electron, actually m is mass of the electron, so it is constant, so the whole thing is constant. So we have this quantity, this is a constant quantity, we call this A0, A0 is called the Bohr radius, that is a constant value. And we know from this equation that the orbit is quantized, and if we put value of z for different atoms and different values of n for different number of states, we will get r. Again I am using equation 2, which is mv square by r equal to z square by 4 pi epsilon 0 r square. I am multiplying this equation 2 with r by 2. What I got is the expression of the kinetic energy, which is half mv square. We got half mv square equal to z square by 8 pi epsilon 0 r. Now I also have from equation 1 that total energy is equal to kinetic energy plus potential energy. Potential energy is Coulomb. Potential energy is due to the Coulomb force, and which tells me that the potential energy equal to minus z square by 4 epsilon 0 r. So I have for total energy this expression. I am just substituting the kinetic energy term from this equation, and I got total energy E equal to minus z square by 8 pi epsilon 0 small r. If we substitute for r, which I have already found, I get E equal to this one. So if I substitute the value for A0, I get this. This term is a constant, this is called Rydberg constant, and it is a value of 13.6 electron volt. Here I can see that the energy of the electron is quantized. If I put z equal to 1, I get the energy, and if I put n equal to 1, 2, 3 or etc., then I can find out the different energy values for electrons orbiting at different orbits around the nucleus. So here a very important thing we came to know, that energy is also quantized because of this n value. Energy cannot take just any value whatever I wish. It takes only some quantized values. Now let's discuss the application of Schrodinger equation. In 3D actually, first we just solved it for 1D, but if I want to write it in proper form, then I need to write all the coordinates in the Cartesian form. Then I need to write the potential. Psi is the wave function which contains all the information about the system itself. This is E psi is the energy of the electron, and we have solved that the energy of the electron is minus me to the power 4 by 8 epsilon 0 square h square z square by n square, where h is Planck constant, epsilon 0 is permittivity of free space, and so on. I have just explained it. And so this is my constant term, which is the Rydberg constant, and value of it is 13.6 electron volt. Now what does this expression tells us? It tells a very important information about any atom. The atom which contains Z number of electrons will have this much of energy, and this is variable with n, which means with the change of n value E changes. N is an integer, so accordingly E will take those values, not just any random value. For hydrogen atom we need to put Z equal to 1, so it's E equal to R by n square. R is a constant, so there is a restriction in the energy of the hydrogen atom itself. The electron inside the hydrogen atom cannot take just any value as it wishes. It has to take this energy values permitted by this relationship. So for Z equal to 1, I have drawn the energy levels for the hydrogen atom. Here I have plotted n equal to 1, n equal to 2, and as we put n equal to 1, I will find that it is minus 13.6, that is the value of the Rydberg constant itself. And if we put n equal to 4, then this quantity is divided by 4. So 1/4 of this is minus 3.4, and so on. So if we put integer values of n, I will get this much of energy, and all these are in the negative side of the energy value. If I put n equal to infinity, then only I will get 0. And if I put here, if I put the electron, then it is eligible to be a free electron, to leave this system if the electron is here only. But in all these energy levels, these negative energy values suggest that the electron must be a bound system, and this energy level shows us that there is a constant in the energy. Electron can reside here, electron can reside here, 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 but not here, not here, not here, not here. Now how this electron can move? This electron is able to move when I supply energy from outside. How I supply energy from outside? I throw some light, some photon coming from outside, and an electron residing at n equal to 1 takes this much amount of energy, and then it makes a transition from n equal to 1 to n equal to 2. But we all know that every system in this universe wants to stay in a minimum potential energy configuration, which makes this electron make a further transition from n equal to 2 to n equal to 1. And this energy difference between this level and this level will be coming out of the system. And as we know that E is quantized because of this relation, there is a restriction on the energy value E. And we know that energy E equal to H into F, F is the frequency. So as E is constrained to have certain amount of energies only, F is constrained to have certain amount of values only. So if E can take a particular value, F has to take a particular value. So its frequency is also constrained. So for E precise, frequency has to be precise. Now how we measure the energy of this outgoing photon? Can we measure this? Is it susceptible to experiments? Yes, it is susceptible to experiments. There is a very simple experimental setup. We just have a glass tube and fill it with the hydrogen gas, then put some electrodes, make some electric discharge, then hydrogen electrons will make a transition from the upper levels, and during the transition to the lower level it emits light, that light is getting emitted from this glass tube. If we make this outgoing light fall on this prism, and as we know, depending on the frequency of light, prism splits the light, white light itself, or the light itself, it splits all the frequencies. So after coming from other side of the prism, a spectrum can be obtained in which there are several lines. One is red, one is green, this must be G, I'm sorry, one is blue, and one is violet. And we know, as these are a particular these colors, these lines are having a particular frequency, so from this relation we'll have a particular energy value corresponding to all these lines. Now what does this lines actually tell to us, these colored lines? What we are getting in the spectrum of hydrogen atom: if an electron makes the transition from n equal to 3 to n equal to 2, then we get red line. If it is from n equal to 4 to n equal to 2, we'll get a green line. If the transition occurs between n equal to 5 to n equal to 2, we get a blue line. If we get transition from n equal to 6 to n equal to 2, I will get a violet line. But what about the transition from n equal to 2 to n equal to 1? As we can see, this is a big energy gap, bigger than these gaps. Let me tell you that for convenience of drawing, I have just drawn the lines like this, but otherwise it will get more closer like this. So as we go up with the n values, the levels will be more closer. More close. So this is my lines, what we are getting in the spectrum. This energy gap is so much that the photon coming out of this transition will give us a spectrum or a line in the ultraviolet region. And we cannot see with our naked eye. We need an ultraviolet camera or something like that to see this photon. And what about an electron makes a transition from n equal to 6 to n equal to 5? Well, this energy gap is so small. So and if what if it gets a transition from n equal to 7 to n equal to 6, say, then the energy levels, the gap between the energy levels is so small that the photon correspond to, photon coming out with that little energy will be in the IR, that is in the infrared spectrum. Now heat is actually infrared. We can see the heat, we can feel the heat. So for n equal to 2 to n equal to 1, we get a photon which is in the ultraviolet region. And for higher energy levels, which are very close to each other, we'll get infrared spectrum and so on. Now this spectrum gives us the answer that why electrons cannot spiral around nucleus, why it just can't take any values. Just spiraling and then jumping into this nucleus is not possible. Because for that case, in this case, we'll have a continuous energy levels, continuous energy. But here we can see we only have definite energy levels. These are the definite energy levels. So this spectrum is an experimental fact that electrons are not spiraling inside the atom, and they are residing only in particular energy levels, that is the energy levels, discrete energy levels with a definite value of energy. This is also explaining the photoelectric effect, which tells us when a photon hits a metal, then some amount of energy of this photon will be used up in the work function of this metal, and then the rest amount of energy will be given to this electron. Work function is, suppose an electron is sitting here in a chair in a metal. When it tries to get liberated from the surface, this is empty, so we can think of a positive charge here, so there is a positive negative attraction, so electron will not be liberated so easily. So in order to overcome this attraction, some energy of the photon must be supplied to overcome that, and the rest of the energy will be delivered to this electron, which will be liberated from the metal. And this particular energy states tell us that what will be the exact amount of photon to liberate an electron in what state. Like if we want to liberate an electron from n equal to 2 state, we need to supply a photon with that much of energy.